Not already on. Testing. You got it?
I think so.
Welcome. We're glad you're here. Are we ready? Are we ready, guys? Okay, let me have your attention. Let's begin. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I introduce today's speaker, I want to make a brief announcement. Today, for the first time, we are migrating to a new technology for the delivery of our webcast. And we've done 2 demonstrations, and we think we have all the bugs out. But Murphy's Law will probably rear its ugly head and get us, and we ask that you be patient with us. The idea in going to the new technology is to provide a much finer resolution so you can see the slides a lot better on both the real-time webcast and also the archived webcast. Okay? Now for introduction of today's speaker, who is Dr. Harold Knox. He is a senior physicist at the Knowles Atomic Power Laboratory in Schenectady, New York. Harold received a BS in physics from Ohio University in 1964 and a PhD in nuclear physics also from Ohio University in 1972. He subsequently served 2 postdoctoral appointments, one at RPI and Rensselaer Polytechnical Institute, and also at Texas A&M. He then returned to Ohio University and served on the faculty there from 1978 till 1988. And in 88, he joined CAPL in New York, which is a naval R&D facility. He's been at CAPL since 88, and he's their local expert on the history of the chart of the Nuclides. And indeed, that is his topic today, historical development of the periodic table and the chart of the Nuclides. So ladies and gentlemen, please welcome Dr. Harold Knox.
Thank you. I gather you all are familiar with the chart. It comes in a couple forms. One is a book like this. The other is a wall chart. And I gather you have some wall charts floating around the lab here. Another technological problem here, apparently we have differences in Microsoft products. This should be historical development over here of the periodic table and chart of the Nuclides. So I think there's going to be some little glitches like that throughout the talk. I don't know whether you noticed the cartoon. We're not going to start as early as the caveman with this, but we are going to start with the ancient Greeks. And man's first speculation on what the composition of matter was, at least the first written documentation, occurred with the ancient Greeks, and in particular Democritus postulated that there were 4 basic substances from which everything else was made out of. The substances were air, earth, fire, and water. Keep in mind, Democritus was not a scientist, he was a philosopher. So this information really wasn't based on research at all. The Greeks also, though, hypothesized that all matter was composed of some small particles, and these were called atomos, from the Greek word meaning indivisible. The theory developed, if you will, and qualities were assigned to these substances. The qualities were hotness, wetness, coldness, and dryness. And so if we had to put together maybe a chart of the substances back then, it would look something like this. Air, earth, fire, and water would be at the vertices here, and the qualities, hotness, coldness, wetness, and dryness, would be the things that attach the substances. Well, not much happened as far as developing these theories for a long time. But through the Middle Ages, alchemy was practiced. And the intent of this was to convert base metals into gold and silver to get rich quick. There was but not much science in it. There was a little chemistry, there was a bunch of astrology, there was some philosophy, and there was a lot of secretiveness. Again, if you were going to strike it rich, you didn't want everyone else to know how you did it, so you tried to keep your work, under covers. They had some interesting symbols they used to represent the materials they were working with. And as far as actual science goes, not much happened during this time. And no one was successful in getting to the gold either. The big changes started happening between about 1600 and 1800. And I've listed three names here: Robert Boyle, Lavoisier, and Dalton. That's not to say they were the only people involved in this. There were other significant scientists involved. But during this time, the foundations for chemistry were established. The ancient Greeks' beliefs about air, earth, fire, and water were refuted. The concepts of elements and compounds were established. Lavoisier, in particular, insisted on quantitative procedures being used in chemistry. He's called the father of modern chemistry, and it's because of his start that chemistry got where it did as quickly as it did. So the actual foundations of chemistry were started during this time. Along with procedures and things like that, John Dalton came up with a way of representing the atoms, and I want to stress atoms here. He had signed a symbol for the atoms of each of the elements. And with these symbols, one could write a chemical reaction. Here, the reaction for one atom of mercury combining with one atom of oxygen, giving mercury oxide. So this was something that had not been done before. You could write equations this way. And this seemed to catch on for a while, for about 10 years or so. And then Berzelius came up with another suggestion, and that was to use letter symbols for doing this by taking the first letter of the name of the element and then a letter from the interior of the name and using that as a symbol. So here's, instead of this equation, here's how one writes the same reaction according to this new formalism. The word, the Hg for mercury, comes from a Greek word which I'm not going to attempt to pronounce, but that's where the Hg comes from. It stands for liquid silver. Okay. Excuse me. By the early 1800s then, about 40 elements had been isolated. And 40 is enough that one can start looking at trends and similarities and dissimilarities between all the elements. And a couple trends were found. One had to do with relative masses. And two studies were carried out independently, one by Dalton, one by Berzelius. And what they did was determine the relative masses of the known elements. Relative to hydrogen, this is. Hydrogen was believed to be the lightest element, and so they took that as kind of their base case. What they found, what both of them found, here's another difference. That should be a dot. Both studies found that the relative masses were integral. In other words, like if hydrogen was 1 mass, carbon might be 12. So they thought all the masses were integral. William Prout then, in 1815, came up with what's called Prout's hypothesis. And he said that based on what they had seen with the measurements, that perhaps all of the elements were built up from hydrogen. So hydrogen would be the simplest. Carbon would be like 12 hydrogens put together somehow. It turns out this isn't true. Later on, more precise mass measurements showed that this wasn't correct. But this was kind of the first attempt of man to try to figure out maybe what the structure of the atom was. And so it's worthwhile mentioning in that respect. The other thing where similarities were noticed were in chemical properties. And it turns out there are several groups of 3 elements. Calcium, strontium, barium is one. Chlorine, bromine, and iodine is another. And if you look at the chemical properties, let's say if you know the chemical properties of two of these, you can predict the chemical properties of the third, either by extrapolation or interpolation or whatever. And this was very curious. People didn't really know why you could do this, but nevertheless they were looking at this group of 40 or 60 by the mid-1800s elements that had been discovered, and trying to pick out similarities and trends in what they saw. As they were doing this, there were new techniques that were being developed to study these things. Optical spectroscopy was one of them. In this, one takes a source of something, you heat it up, you pass the light that is emitted by that through some slits into a prism, and that light is broken up into discrete lines. And people weren't sure why there were discrete lines. Nevertheless, they started looking at a bunch of different materials. And Bunsen and Kirchhoff came up with the statement that every element is characterized by a unique optical spectrum. And in fact, the two of them discovered two new elements. One was rubidium, and the other, I think, was cesium. And it was based on the spectral lines from these two materials. This is a sketch of the apparatus, if you will, that they used. There's a prism in the middle. This is some kind of a viewing tube, if you will. The prism was rotated down here as opposed to having film in here. The sample was located over here. This is a burner, if you will, invented by Mr. Bunsen, that was particularly adapted to this because it was a nice clean flame and they could get good results. Maybe you're familiar with, with that burner. The simplest spectrum was that of hydrogen. And the spectrum looks something like this. Again, these are all the lines that are in it. It was first studied by Anders Angstrom in 1855. He looked only at the visible part of it and saw 9 lines in it. Some 3 years later, Balmer, who was a mathematics professor in Switzerland at a girls' college, showed that the wavelengths could be expressed by this equation, where B is a constant and N is an integer that could take on values between 3 and 11. He was told a few years later that additional lines had been observed by looking at the spectrum from the sun. These were not visible. These were like ultraviolet lines. But Balmer showed that his formula worked for those also. Balmer was about 60 years old when he did this. He published 2 papers in his life, and we're still talking about him today. Oh, that life were that way. Okay. Balmer's work prompted other scientists to pick up where he had left off and look at more complicated materials and spectra. Redbird did a lot of this work, and Redbird was successful in coming up with other formulas that predicted, that gave the wavelengths of the lines of these very spectra. But he came back to Balmer's formula. It turns out Redbird liked to express things in terms of the wave number instead of the wavelength. And he rewrote Balmer's formula in a slightly different form. Here, R sub h is the Redbird constant. There's a 1 over 2 squared minus 1 over n squared. It's equivalent to what Balmer originally published, but it's slightly different. And remember the form of this because we're going to come back to it later on. The R sub h here is called the Redbird constant for hydrogen, and it was determined experimentally, just, if you will, by fitting the data. Okay. Dmitri Mendeleev was a Russian chemist, and he seems to have been preoccupied by trying to discern the similarities and trends of all the elements that were known. Apparently he had little like index cards that had the names of the elements on it and their properties, and he spent a lot of time shuffling these cards around, trying to look at trends, trying to see overall was there a picture to how the elements were put together, if you will. In 1869, excuse me, he came up with what was called his periodic system, and this is a bit different than what we're used to. This had what was called a vertical form, and he arranged all the known elements on these little cards, if you will, in vertical lines. And if one looked at rows across this, usually the elements that were across a row had similar physical character or chemical characteristics. He arranged these elements in these vertical columns according to mass. And I said sometimes these things on rows had similar chemical properties, but there were pairs that did not. And Mendeleev didn't like this, but he wasn't really sure what to do. So he pondered things for a few years and came out with another form of a periodic table. This is a horizontal form. We'll see what it looks like in just a second. But here he arranged the known elements in rows, ordered by chemical properties. And where he thought there were elements missing, he left gaps. And so his table looks something like this. Not something like this. This is the table. But he has, 8 columns, if you will, called groups. He determined what went into which column by the type of compounds that formed with either oxygen or hydrogen. The ordering, again, is almost by mass. Here's hydrogen, mass 1, lithium, mass 7, beryllium, mass 9.4, and so on. Those are the masses after the chemical symbols. The triads, can you see the gold? The triads that we talked about earlier are here: calcium, strontium, barium, and over here chlorine, bromine, and iodine. So, okay, this thing. All right, this will make marks, right? Okay, well, where was I? Okay, the triads are here, and they are in columns, so the chemical properties are similar. But the gaps that were left were here for mass 44, mass 68, and mass 72. And Mendeleev believed that there should be elements with those masses. From the table, he predicted the properties, the chemical properties of these masses. And within about 10 years, all of them were found. They were scandium, gallium, and germanium. Okay, a couple other things of interest. If you'll see, copper, silver, and gold are over here, and they're also over here. Mendeleev wasn't sure exactly where to put them, and so he put them in 2 places. He knew one of them was wrong. As it turns out, this column is the right column for them, but at the time Mendeleev didn't know. There's also another class of elements that have question marks in front of them. There are 5 of them in here. And these were elements that Mendeleev wasn't sure if they were in the proper place. One of these was called Diadem Ium, and it turns out that's not an element at all. It's a mineral that for a while people thought was an element. But he's done a good job of getting everything together. And there are a couple problems with copper and things like that. But when all the blanks were filled in, would his table be complete? Or might there be some surprises? Well, it turns out there were some surprises. There are 2 of them. The first one was the inert gases. And up until the late 1800s, no one really knew that these existed. But they were discovered, I believe, in spectroscopic studies of light from the sun. And all of them, once the first one was discovered, the rest of them fell into place very quickly after that. The other surprise had to do with the elements that were in green on the periodic table. And this has to do with what's called the rare earths. The earths were some metallic oxides that chemists had known about for a long, long time. But in the late 1700s, early 1800s, two new earths were uncovered. One was named Yttria because it was located in mineral deposits near Ytterby, which was a village in Sweden. The other was named Syria, and I'm not really sure why that name was given. But these two oxides were called rare earths. And the reason they were given that name is because it was believed originally that the number of geological deposits, if you will, of these materials were few and far between. That perhaps this only existed in a very limited region in Europe. And so they were called rare earths. Turns out that's not the case. They're found a lot of other places these days, but again, people didn't know it back then. Over the next 100 years or so, 16 new elements were isolated from these two earths. Things like lanthanum, cerium, neodymium. And at first, chemists weren't sure exactly where they should go in the periodic table. The masses of them were all similar, all closely spaced, if you will. The chemical properties were similar. In about 1905, what is called the long form of the periodic table was published. If we look at this, the inert gases are over here. The rare earths are in this section enclosed in red. There are also other pairs of elements here, cobalt, nickel. There's argon and potassium over here. These are cases, here's another one, tellurium and iodine. These are where the elements are placed according to their chemical properties. Their masses are in opposite order, okay? This mass is larger than that mass. It's chemical properties that are determining the order here. Okay, I guess that's all I want. Did I just touch it? Oh, I knew that. Okay. Complicated. Okay. All right. So we're making a lot of progress, but we got fooled once, right? With Mendeleev's chart, it turns out there were complete families of elements that were missing. So is this table complete? Yes, there's still some blanks in there, but are there other families of elements that are missing? And the answer is that scientists just weren't sure. It's because they didn't really know what was causing the ordering of things on the periodic table. It wasn't the masses. There had to be something more fundamental than masses that determined this ordering. Yes, it was related to chemical properties, but what was the cause of the similarities in chemical properties? And they didn't really understand that. Perhaps if they understood the structure of the atom, maybe that would give them some clues to it. So, what did they know about the structure of the atom at this time? And the straightforward answer is, well, not a whole lot. But there were a few things that should give them some clues. And one was the discovery of the electron. It was discovered by Sir William Crookes, by looking at studies of conduction of electricity through rarefied gases. The charge to mass ratio was measured by J.J. Thomson, and Millikan determined the actual charge of it in 1910, and the electrical charge was the same as that of the proton. The magnitude was the same. The sign was opposite. The other thing that was discovered coming from atoms were X-rays, and these were discovered by Röntgen in about 1895. They were shown to be a form of electromagnetic radiation, but again, the cause of either of these, what brought electrons out of the atoms, what brought X-rays out of the atoms, what atoms, was not really well understood. Another curious thing was discovered in the late 1800s, and it started with Becquerel studying the fluorescence of compounds containing uranium. And the story goes that he had some film, photographic film, that he was doing some experiment with. He also had samples of these uranium-containing compounds, and he apparently left them in a drawer together over the weekend, came back, started to do some experiments that needed the film, and found the film was fogged. And he traced it down to being near the uranium compounds, and so he attributed this to some kind of radiation being emitted by the uranium compounds. He wasn't sure what it was. In 1898, Marie Curie discovered a similar thing happening with compounds containing thorium. And this started Marie Curie on a quest, if you will. She wanted to determine what in these uranium compounds was the cause of the radiation. And so she began chemical separations of these compounds, trying to figure out, again, what the source of the radiation was. With her husband, Pierre, they developed the ionization chamber, and this gave them the ability to follow the intensity of the radiation emitted by these materials as a function of time. In her studies, she isolated two elements, polonium and radium. Polonium was named for her native country, Poland, and radium, the source of the name, is from the Latin word radius, which means ray. She also coined another word that you've probably come across, radioactive. And again, the radio and radioactive comes from the same source as radium. It's the word radius, the Latin word radius for ray. And radioactive caught on after this also. Okay, another major player in studying these radioactive materials was Ernst Rutherford. And here, this is also a Microsoft glitch here. They found that there were three types of radiation emitted from these compounds, and they were called alpha, beta, and gamma, the first three letters of the Greek alphabet. The alpha radiation was later shown to be an ionized helium atom. The beta radiation was the same as cathode rays or electrons. The gamma radiation was actually discovered by Paul Villard, and this was a form of electromagnetic radiation. Frederick Soddy, who worked with Rutherford, found that if you looked at the time dependence of the radiation, the radioactive decay, it could be written as an exponential decay. And the lambda, this could be characterized by what was called a half-life, let's say. And this is the time it takes for half of the material present to decay. So the things that they were studying, the materials, the radioactive materials, one way to characterize them was by their half-lives. They could also be characterized chemically. But things were a bit complicated, let's say. And the reason things were complicated was they were actually looking at 3 different naturally occurring radioactive decay series. One started with uranium, another started with thorium, and the last started with actinium. And in these decay chains, they observed about 40 new, and I've called these things species, because they weren't necessarily new elements. And for a while, people really didn't know what they were. They were all named. They had names like ionium, radiothorium, radium A, radium B. And some of these seemed to be chemically identical, but they had different masses. And these 3, radiothorium, thorium, and ionium, was a set of 3 like this. The masses were different, but chemically they were the same. Soddy, again, who worked with Rutherford, said that these 3 materials, along with others just like those, should all have the same position on the periodic table because chemically they were the same. So he called them isotopes. And isotopes, it comes from 2 Greek words, isos and topos, which means same place. So because they occupy the same position on the periodic table, they're called isotopes. So the 40 things that they isolated turned out to be isotopes of 12 different elements on the periodic table. And it took, I don't know, 20 or 30 years for scientists to figure this out. Francis Aston proved the existence of isotopes by taking a beam of ionized neon atoms and passing them through a magnetic field. And the beam split into two distinct spots, if you will. So he concluded that iodine had 2 stable isotopes. Turns out there are actually 3, but the abundance of the 3rd isotope was so small that Aston wouldn't have been able to see it with the equipment he was using. Okay, so the masses of the elements then, and let's emphasize elements here, depends on the masses of the isotopes and on the relative abundances of all of the isotopes. So if we go back to Prout's hypothesis, the masses are not integral because, well, first of all, there are isotopes in here having different masses that are put together with different abundances, and there's more that would cause the difference, and that we don't really know, as far as the story goes yet, what the structure of the nucleus is, and that will change things also. Okay. Whoops. Okay, this period of time, the early 1900s, if you were a physicist, I think they would have been some of the most exciting times ever and probably some of the most bewildering times ever, because a lot of things were happening. It was being shown that classical physics failed in several cases, and it took a while to figure out what was going on. But some of the failures of classical physics had to do with the thermal radiation spectrum of what was called a black body. This is a perfectly absorbing body that, if heated up, would have an emission spectrum that people measured, and they tried to predict with classical physics what that should be, and classical physics couldn't do it. Another problem was with what was called the photoelectric effect. And here, if light shines on certain materials, electrons will be emitted from that material. And with classical physics, they could not explain the energy of the electrons being emitted. These 2 things could only be explained if they assumed that light had particle-like characteristics, and that particle is called a photon, and that the energy associated with the photon was given by this equation, E equals h nu, where nu is the frequency of the light. With these assumptions, one could get an explanation for these 2 effects. The other big thing that happened during this time, one of the other big things, was Einstein published the theory of relativity. And this showed that with the equivalence of mass and energy, among other things, here's a photograph of Einstein that probably is not one of his more popular ones, at any rate. While we were putting together the chart book, the authors got really interested in Einstein and his being able to come up with this new equation. And we wondered what might have been his motivation, what great scientific insight might have led him to this. And we think we found what it was. Oh, well. Okay, on with more serious things. X-ray spectra were also studied during this time by Charles Barkla, was one of the people that had a lot to do with this. And the X-ray spectra have two parts. There's a continuous background part of it down here, and then there are some sharp spikes on top of the continuous background. They named these spikes the K series and the L series. And the reason they did this, Barkla did this, and he thought surely there will be higher and lower energy X-rays found. And he didn't want to start with the A series and the B series. He said, let's start in the middle of the alphabet. We'll call it K and L. Well, it turns out there is no A and B. And if you wonder why K and L are there, this is the story. They thought there was going to be more, and there wasn't. At any rate, in 1913, Henry Moseley started looking at these X-rays, and he looked at the K series of X-rays for elements up to zinc and the L series for elements up to gold. And what he found was that as the masses of the elements increased, the frequency of the X-ray lines increased, but there were irregular variations. If you remember, there were problems ordering things by mass on the periodic table too. If each element, though, was assigned a number Z, according to its position on the periodic table, there was irregular variation. Okay. If we look at these X-ray energies, here's a plot. Again, the atomic number is along the bottom part. The dots are the K and L series. The reason that there's a K alpha and a K beta, and an L alpha and an L beta, we'll discover why that is a bit later. Okay, so masses and chemical properties had been used to determine the ordering of the elements, but there was not really a straightforward way of knowing when to use what, using those two things. But this showed exactly where everything should go. As it turns out, I plotted everything here. When Moseley did it, there were some blanks left in there because they hadn't discovered all of the elements then. So Moseley's measurements indicated directly the proper ordering, and gaps that were in this line showed which elements were missing. So now they knew exactly the elements that they still had to find. Here's a periodic table. Again, a slightly different form. There was an evolution of periodic tables, as you can see. This is set up something like Mendeleev's original table. The inert gases are over here. The columns are similar. The rare earths have been pulled out. The rare earths should go in here. They are pulled out into a separate little box down here. But the ordering now is by atomic number, and there are some blanks in here. Here's one, here's one, here's one. And again, those in 1913, and this is based on the X-ray spectra, the X-ray spectrum. Those were the only elements below uranium that had not yet been discovered. And they knew that with certainty now. They knew what the ordering was on the periodic table. Okay, let's talk for a little bit. We'll get back to the atom and, well, I guess maybe a little bit about the nucleus. We talked a little bit earlier about what was known about the atom. There were X-rays, yes. There were electrons that had to be accounted for. Thomson in 1910, J.J. Thomson, came up with what was called the Plum pudding model of the atom. And in it, he took into account what was known. All atoms contain electrons and commit electromagnetic radiation, the X-rays. Since atoms are normally neutral, they must contain positive charge equal in magnitude to the negative charge of the electrons, and most of the mass has to be with the positive charge because the electrons don't weigh that much. So he came up with what was again called the Plum pudding model, and he proposed the radius was about 10 to the minus 8 centimeters, that there were electrons uniformly distributed throughout this atom, and they were distributed in a sphere of positive fluid of some sort. He didn't really specify what this was. No one really knew. If this atom were excited by electromagnetic radiation or something like that, the electrons in here would oscillate. That would give off electromagnetic radiation. And so most of what was known was satisfied by this model. The question was this model really accurate or not? And Ernst Rutherford tried testing this by the following experiment. He had an alpha source here, a sample of some metal. He used various metals. Here, and a zinc sulfide screen here, a telescope here. This, by the way, is a graduate student. Okay? The Geiger and Margson were two graduate students who did this. They must have spent days looking at this. But the intent was to scatter the alpha particles from this foil and look in various directions at how many alpha particles came out. If the Plum pudding model was correct, most of the alpha particles would pass straight through this way and not be deflected at all. Well, the graduate students looked at this for ages, I think, and they found not that there was no deviation at all, but they found some alpha particles coming back at back angles. And this was totally unexpected. If the Plum pudding model were accurate, that could not happen. So this says the Plum pudding model is not accurate. And Rutherford mulled over these results for a couple of years and decided that he would come forth with a new model of the atom. And in this, he proposed that there was a very small positively charged nucleus, and around that were electrons, much like the solar system, the sun and the solar system. The only problem with this is, in classical physics, this isn't a stable system. The electron, as it goes around the nucleus, is accelerating. Because it's accelerating, it should emit electromagnetic radiation. If it emits electromagnetic radiation, it loses energy, and so it should spiral into the nucleus. This isn't a stable situation. So, again, we go back to problems with classical physics. And we've mentioned a couple of them. Black body radiation, photoelectric effect, the source of discrete lines in the optical, or in optical and X-ray spectra, and this new model proposed by Rutherford is something that cannot be in classical physics. Bohr, nevertheless, proposed another model, and again, he's going to make some assumptions that are contrary to classical physics. He assumed that Rutherford was correct in what he said, and he also assumed that the angular momentum of the electron was quantized. And what do we mean by that? It's that there could only be certain orbits of the electron around the nucleus. If the electron changed from one orbit to the other, either energy had to be put into the system or energy would be given off in the form of electromagnetic radiation. So the discrete lines in the spectra that had been talked about for years, this would be explained by that. Okay, with these assumptions, one can, without too difficult mathematics, show that the wave number for the light emitted by the system is given by this equation. Now, do you remember Rydberg? Do you remember the form of the equation that Rydberg came up with? It was 1 over 2 squared minus 1 over n squared. And there was a constant out front, which was called the Redbird Constant. So with this equation, it's backed up, the results are backed up by experimental measurements. This is the Redbird Constant. If n sub f is 2, this gives the Balmer series of lines. But this n sub f can take on values other than 2. And it turns out other series were found. I think there were 3 other series. Is that right, Paul? But the Balmer, Passion, I forget what they all are. There were other series that were discovered, and it was based on this measurement, or this theory. Okay. Bohr took okay. That's all right. Bohr carried this farther on, and he started studying multi-electron atoms or systems, and he showed that there was a shell structure for the electron orbits, so that elements in the same column of the periodic table had similar electron structures in the outer orbits. The inert gases had full closed shells for the outer shells. They tended, therefore, not to react chemically with other materials. And that the X-ray lines were caused by transition of the electrons from the inner shells to the outer shells. So what this shows, though, is we now have an understanding of the chemical properties of the electrons. We understand optical spectra. We understand X-ray spectra. The icing on the cake came in about 1926 when quantum mechanics was developed. And with quantum mechanics, this stuff all falls out. There isn't a need for making weird assumptions. Quantum mechanics makes some different assumptions to start out with. But okay. One thing that hadn't been covered, though, or hadn't been figured out, was what was the structure of the nucleus. And early on, let's say early on, a proton-electron model had been proposed for this because those were the particles that people knew about. And with this, the mass should have been provided by protons with the electrons balancing the charge. What changed all this was, though, in 1932, Chadwick discovers the neutron. And once that was discovered, almost immediately, Heisenberg came up with a neutron-proton model of the nucleus. Here, the nucleus consists of Z protons and N neutrons. The mass number is N plus Z. Isotopes have the same number of protons but different number of neutrons. And so finally, all of it makes sense. We understand isotopes, we understand elements, most everything. In 1932, Irene Curie, the daughter of Marie and her husband, bombarded an aluminum target with alpha particles. And after the bombardment had ceased, they noticed that the target was radioactive. And this seemed curious. What was happening, though, was there was a nuclear reaction going on, this being that alpha's incident on aluminum-27 formed a neutron plus phosphorus-30. Phosphorus-30, oh, I didn't mention one thing. They found that the half-life of the radiation coming from this stuff was about 3 minutes. Phosphorus-30, as it turns out, isn't a stable nuclide. It beta decays with a half-life of 3 minutes. And so these people had done something new. They created an isotope that didn't exist, that doesn't exist in nature. And they called this artificial radioactivity. But if you think about this particular thing, then there must be a whole lot of other reactions that one could do that would lead to other radioactive materials. And what there are. And what happened here was this brought about the development of particle accelerators to study all sorts of reactions leading to artificially produced nuclides. So now, yes, there were all the stable nuclides that were known, but man started generating unstable nuclides that stuck around for a little while. And in 1935, Fay, who was a graduate student of Emilio Segre's in Italy, published what he called the neutron-proton chart. And it's really the first chart of the nuclides. He plotted proton number down here, neutron number up here. And I don't know whether you could read these. Squares correspond to radioactive materials. And then he has 3 different types of circles that show the abundance of stable isotopes. And I've only showed a little bit of it. He looked at everything up to uranium. And so this was the first, if you will, chart of the nuclides. I don't think you can see this. I don't intend you to be able to read it. But this is a current chart of the nuclides. I wanted to point out that without what Irene Curie and her husband had done with artificial radioactivity, we wouldn't have been able to fill in the chart of the nuclides. The periodic table, because there are some elements that only have radioactive isotopes. There are no stable isotopes. Technetium is one. Promethium, is that it? I'm talking about up to uranium. I think that's it. But it took the artificial radioactivity thing to allow us to fill in the whole periodic table. Okay, we mentioned one chart of the nuclides. I want to talk a little bit about the Capel chart. Again, this is the 16th edition of it. The first edition was published in about 1948. The editors were Gerhard Friedlander, who's published many radiochemistry textbooks. And he just retired from Brookhaven here 5 or 10 years ago. Friedlander was one of Glenn Seaborg's graduate students. And as a graduate student, one of his duties in Seaborg's research group, this is back around the time of World War II, was to maintain a chart of the nuclides for the research group. Various groups kept their own. And when Friedlander came to GE, he started keeping one there. The format differs from the Fay chart that should be, in that the axes are reversed. And we still go that way today. Z is up here, N is the horizontal axis. As new elements and isotopes were discovered, subsequent editions were published. Capel took over the production of this in the early 50s. I should know the date and I don't. It's like 53, 54. And the last slide is, this is a portion of the chart which you see up here. And I will take questions if you have them, or
this presentation is now open for questions and comments.
This is a strange question, but when the Bohr model replaced the Plum pudding model, you made the point that the features are always like it wasn't dynamically stable. Is the Plum pudding model dynamically stable?
I think so, yes. I think it was. I don't see anything that violates, offhand I don't see anything that violates some principle of physics.
Did anyone ever make predictions from it? Like what would happen when an electron was emitted?
That I don't know. I don't. It explained the obvious things. It explained that there could be electrons given off. It explained what there could be X-rays given off. What the size was about right. I'm not sure how they would have guessed the size, but it explained what was known at the time. But it didn't take long before it was shown this couldn't be the case. Rutherford's alpha particle scattering experiment blasted it, put it that way.
Other questions or comments? Please use the microphone.
Is it switched on?
Yeah.
This is a kind of a trivial question. I'm just curious. When Bunsen invented Bunsen burner, do you know what kind of gas he would have been burning?
I don't have any idea.
No, me either. I don't know when coal gas came into use.
I didn't realize Bunsen had been involved in this until we started doing the research for this thing. And we kind of got, I don't know whether you've looked at the stuff in here. We have a couple hundred references on stuff like this. And there were 3 editors. We almost got reprimanded for taking too much time on this because we were off looking at interesting stories like this very thing. And no, I can't answer your question. If I were allowed to spend more time on this, maybe I could have answered it.
I'll write to your lab director if you like.
I don't think we should do that.
Oh, right there. Okay.
There's also a chart of the nuclides that's published by Karlsruhe. Where does that fit into development
There,
of the chart?
I think, are 3 other paper charts, and there are some electronic charts. The Karlsruhe chart shows more information, I think, about decay modes. There isn't much on neutron cross-sections or anything like that. So each chart has its own flavor of what information the authors think are important. The CAPL, we're interested in neutrons, so we have neutron thermal cross-sections on it, as well as some decay data. So there's a Karlsruhe chart, there's a Chinese chart, and there's another German chart. I can't think who publishes that. Yeah, I can get some more information to you when I get home. I don't remember where everyone is. But there are, like I said, 4 paper charts out. And then if you get on the internet, there are a number of electronic charts. And we are hoping with the next edition of the CAPL chart to have both a paper chart and an electronic chart. But we'll see what. This is not CAPL's primary product. And it's, if we can get the money, there will be an electronic chart. But again, CAPL does other things also.
Yes.
When I looked at this chart earlier, they used to talk about going to a universal naming convention for the newly discovered elements. And on this one, they're not. I was just wondering.
If you look at, you're right. It's something we haven't included on this. But if you look at the unnamed nuclides out in here, yes, IUPAC, the International Union of Pure and Applied Chemistry, has a naming convention that they use out there. We don't put it on. And I don't know why we don't do that. Maybe in the next edition we'll keep that in there.
We have other questions or comments from the audience? I have one having to do with it. This is a real service that CAPL provides to the entire scientific community, but surely it comes at a cost. And my guess is that the Navy is absorbing the cost and the overhead. But do you have any idea what providing this information to the world, what it costs annually, for example?
Well, it's only done like every 5 to 7 years. And manpower-wise, 4 people at CAPL put it together. There are 3, there's a nuclear physicist, that's me. There are 2 radiochemists. And we gather the data. Actually, we have a database that has all this stuff on it that we keep adding to. Then there is 1 woman that does all the graphics. And so it's like 4 people for about 2 to 3 years every 5 to 7 years. The cost of printing the chart, when we used to be part of the GE organization. And at that time, GE would pay for the entire printing of the chart, and they handled the distribution of it. We're now part of Lockheed Martin, and they are doing essentially the same thing. So as far as CAPL and the Navy goes, we're paying salaries for 4 people for 2 to 3 years.
Okay.
And that's about it.
Okay. Before we adjourn...
I have
okay.
one more thing to say. The authors kind of get frivolous, not frivolous, get carried away. You notice I have a chart of the nuclides. Hi. We also have a chart of the nuclides T-shirt that has the chart symbol up here and the radioactive decay chains here. And I would like to present you with a genuine chart of the nuclides.
Thank you. Okay, before we adjourn, there's one person that I feel like we should recognize. Most of the nuclear engineering students and the faculty, of course, are quite familiar with the Barn book, which is the original paper edition of nuclear cross-section data. And we have in the audience today one of the original authors of the original Barn book, and that's Mr. Jack Harvey, and I want him to stand up. Let's give it up. Round of applause. Okay, and as always, we have a few new faces in the audience, and everyone is invited to our reception, which is downstairs on the 2nd floor. Dr. Knox and Dr. Harvey will be down there to answer questions one-on-one. But before we adjourn, let's express our appreciation again to Dr. Knox for his presentation.
Thank you.